Okay, so now it's open?
Yes. So
All
let's
right.
wait some minutes, okay? A couple of minutes, and then we can start. Okay, so let's get it started. So thank you for joining us today in our fourth session of the virtual seminars in economic theory. Today we have with us Professor Eliaz from Tel Aviv University, and he's going to talk about cheating with recursive models. It's a joint work with Ran Spiegler and Jer Weiss. And last but not least, we have with us as invited panelist, Professor Ignacio Sponda, okay, who is also expert on the topic of today's talk. Before I hand over to Professor Eliaz, let me remind you that these seminars take place every Thursday at 4 p.m. UK time. And as usual, you can find more information about the coming list of speakers in our website. The format of these seminars is as follows. It's going to be 60-minute presentation with time for interim questions, followed by 15-minute discussion of questions. It's a public chat in which you can ask questions along the talk, okay, and we'll try to pass the questions to the speaker. Or maybe at the end, or at the end is going to be also 15 minutes for questions, for additional questions, and you may be leaving the possibility of making your questions live. So thank you, Kefir. The floor is yours, or the screen.
Okay. All right. Thank you very much for including me and my co-authors in this program. So this is part of a broader agenda that Ronnie and I have, which studies how misspecified beliefs of economic agents may arise endogenously through the strategic actions of other agents. So this is one part of this agenda. And the starting point of this talk is actually an obvious observation that, quantifying correlations between random variables preoccupies policymakers, managers, and us researchers for a variety of purposes, be it diagnostication, prediction, when we engage in causal reasoning. And measuring these correlations can be done either directly from the observed data, but oftentimes it's done actually indirectly via the use of models. And this is going to be the focus of this talk. And let me first try and maybe explain the obvious, why we sometimes resort to models to indirectly measure correlations between random variables. Okay, so one obvious reason, of course, is when we don't have the data on the joint distributions of the variables of interest. So, for example, this is common in medical research when a pharmaceutical firm develops a new drug and it wants to understand, what's the long-term effect of that drug. Of course, it doesn't have the data on the long term of a brand new drug. And so it resorts to using biomarkers to indirectly estimate the relation. Also in economics, if we want to understand, the relation between, say, market structure and tacit collusion, tacit collusion is not something we observe from the data. We often rely on models. And I think, recent events also exposed us to extensive use of, models to try and understand, how measures like lockdown or social distancing can affect, a spread of a brand new virus, which we don't know much about. And so that's one obvious reason. Another reason, which is also quite common in economics, is when we want to understand causal relations, right? So we know that observed correlations between variables don't represent a causal effect when they're partly due to confounding. And one way to overcome this confounding effect is to postulate a structural model. Related to that is when we engage in covariance estimation. So, the most natural and estimator you could think of, which is just a sample covariance matrix, performs actually poorly and can lead to invalid conclusions in high dimensional settings. And again, one way around this difficulty is to impose structural assumptions. And even in low dimensional settings, sometimes we can improve estimation by imposing restrictions that are implied by a structural model. So for instance, if we're interested in estimating demand, as a response to prices, sometimes we can improve the estimate if we actually impose that the demand is downward sloping. And even when we can reliably measure correlations directly from the data, from data, say we ran a randomized experiment, oftentimes we're not satisfied with just the mere measurement, and we want to understand the mechanism, the underlying mechanism that transmits the causal effect or that creates the correlation, because this sort of helps us, gives us a sense that we better understand the effect. And of course, it also suggests opportunities for future interventions. And one way to do that is through a causal model that organizes the empirical regularities into what you may think of as a narrative or a story of which variable causes what. And this, helps us better communicate and remember these empirical regularities rather than just looking at, covariance matrices or statistical tables. So for all these reasons, models can be quite useful at, quantifying correlations between random variables and helping us understand the implications of them. But this is provided that the models are correctly specified. Misspecified models, on the other hand, can lead to erroneous beliefs, which can then, lead to very poor decisions. And so really what we want to understand in this paper is to what extent, how distorted can our beliefs be? What's the limit of the distortion as a result of model misspecification? Or put it a little bit more specifically, is to what extent can a misspecified model create a distorted estimate of pairwise correlations? And, you know, a natural question is why, you know, why would we want to, well, why should we be interested in that question? So one answer is actually that by now there's a large literature in theory that tries to model interaction between agents who have misspecified models of the environment. You know, Ignacio, our panelist, has a series of works on this. Here I mentioned his work with, his first name is Daniel, I always forget, Puzo?
I was muted, sorry. Damian Puzo.
On Burke-Nash equilibrium. Philippe Giel has a series of papers on analogy-based expectations, and my co-author Ronnie has a series of papers that tries to represent causal misperceptions through the use of Bayesian networks. And of course, there's a large literature in macro, in robust control about, you know, how to take into account a regulator's, the possibility that he has a misspecified view of the environment. And so basically what we do in this paper could be thought of as an introducing worst case analysis, understanding the limit on how badly or how off can the beliefs of these agents be. You know, is it something that we should be worried about? Can they be really distorted, or it's not something that even in the worst case, the beliefs are, you know, are not way off from what they should be. So that's a purely theoretical motivation. A second motivation is, you know, as we all know, politicians, you know, and experts often try and influence public opinion through the use of, you know, false narratives, which you could think of as a misspecified causal model. So that they try to shape public opinion regarding some policies, you know, you could think of climate change or the impact of immigration, or to attribute credit or blame to predecessors. And in fact, Ronnie and I have a recent paper that tries to model this and understand how false narratives can endogenously arise when there's competition over public opinion. And so this paper sort of takes a step to understand to what extent can the public opinion be manipulated? You know, how, you know, what's the extent to which the beliefs can be distorted by such false narratives? Another related issue is that, you know, when there's multiple competing models that try to address some, you know, social issue, oftentimes, you know, those that predict extreme effects, for example, large correlations, are more likely to be salient, right? And so this is another, you know, trying to understand, you know, what's the most extreme effect you could create with a misspecified model. And so there's also a recent paper about competing models by, I'm not sure I can pronounce the first author's last name, I think it's Jose Montiel or Lia, but it's joined also with Pietro Ortoleva, Malish Pai, and Andrea Pratt. And then I think closer to home, you know, we researchers, you know, oftentimes try to persuade audiences of either diagnostic, predictive, or causal relations between variables, either because, you know, the researcher is serving some policymaker with an agenda, for example, trying to show that tax cuts are good for growth or that immigration is bad for employment, or because the researcher is trying to make a splash by showing some really big effect, or because he stakes his, you know, he made his reputation by showing some, you know, correlation between variables, and now he's trying to, you know, when making his further research, he's sort of even subconsciously biased to show this correlation. And in what I'm going to, in moving forward in this talk, I'm going to sort of adopt sort of this story of the opportunistic researcher who tries to persuade an audience through what you might call model hacking. Okay, so by that I mean that think of an analyst who wants to persuade a lay audience. Yeah, so I'm not talking about like a room of econometricians. That one variable is strongly correlated with some other target variable y. Right? You can think of this as sort of a causal persuasion, right? So there's a policymaker who will take some action only if he's presented with sufficient evidence that this action causes or is related to some outcome. And so our analyst is actually proceeds, scientifically. He builds a model that contains the variables of interest x and y and some other variables, and then he estimates this model against real data. And again, why he's using a model, I've already given you a couple of reasons. And then this analyst is sort of proceeding scientifically. He's not tampering or playing with the data, but his only discretion is that he's free to decide which variables enter his model and how these variables enter. I see there's a couple of chats there, so is there questions I should take right now?
Oh, sorry, there was just a bug that the chat was off for participants. So that was all.
Okay.
So they couldn't. Yeah.
Okay, so back to my analyst. So as you see, of course, the question, in order to be able to say something about what our analyst can do, the extent to which he can persuade his audience, of course, I need to understand, what type of models he can use. What is his feasible set? Otherwise, I won't be able to say anything, let alone do, show you some analytic results. And so we're going to take the set of admissible models that our analysts can use to be those that take the form of recursive systems of linear regression equations. So linear regressions, we know what they are. What we mean by recursive means that the explanatory variable in one equation can't appear as a dependent variable in another equation down the list. Okay, so we don't have feedback or simultaneity. And the model is going to include the variables of interest x and y and up to n-2 additional variables, where n is going to be a parameter that's going to measure the complexity of his model. And then each of these equations is going to be estimated via OLS. And so why do we focus on this class of models? So one reason is that it's actually familiar to us economists. I mean, in a sense, it's a special case of simultaneous equations, which we all know very well. Of course, here the recursiveness takes away the simultaneity. Outside of economics, actually, these class of models are well known. They go by the name of Gaussian Bayesian networks, because they can actually be described by a directed acyclic graph, and I'll show this later. And since the influential book by Judea Pearl, these models are really this class of model is like the leading formalization of causal models because of the recursive nature. So if x is an explanatory variable of y, and there's no feedback from y to x, you could interpret correlations between x and y whenever x is an explanatory variable of y as actually a causal effect of x and y. And this class of models is regularly used by empirical researchers. So in economics, today we mostly use the most simplest one, which is just a single equation. In medicine, as I alluded to before, the use of biomarkers is one example of a recursive system of equations, which I'll show you in a second. And in biology, more complicated systems are used to delineate gene networks. But really, during this talk, I also want you, to take the view that that this class of models, the way we also view it is, we're not trying to map one-to-one what, modern day econometricians do. We view it more as a stylized representation of empirical research. Just like, when you write down, infinite repeated game of price competition, you don't pretend that this is the mapping of, how firms compete in reality. It's just your labbed or stylized representation. Usually we don't even say this, but because, I'm going to use terms like regressions, it might give the impression that we're giving sort of a critique of how current econometricians are employing their methodology. But what I would like you to think of is just we're modeling how an how a stylized econometrician works. And, and just as as I mentioned before, in Bayesian persuasion, we use the stylized model of a sender who commits to a signal structure to try and manipulate the receiver's beliefs. Here you can think of this, and by analogy, the analyst who uses a misspecified model to try and manipulate the beliefs of his audience. Okay, so that's another way to think of what we're doing. And as you'll see, this class of recursive models, of course, is very tractable and analytically convenient. Okay, so
here, if I may, Ignacio,
sure.
here, if I may just add maybe an idea for motivation for recursive models. You're saying one of your questions of interest is how to convince a layperson, give them a story that there's a correlation between two variables. And it seems to me that recursive models have this sequential structure that almost tell a story. That yes. Is like a simple story. And I wonder perhaps if maybe linguistics have more to say about this, but how exactly do you tell stories? How would you capture that? And I think, I don't know, it looks like recursive models have this nice feature like, okay, this thing causes that, and then yes. That other thing causes this other thing, and tell like a linear sequential story that is easy to tell.
Yes, so you're absolutely right. So, simple ones, as I'll show you, with the simplest recursive system is like a chain where, one thing, X causes Y, which causes Z. Of course, the models could be more complicated, but as you said, the recursive structure, because it lends itself into a narrative, right? These set of alternatives cause this, and this causes this other thing. So I think you're absolutely right. I don't know much to say about how, it's used in textual analysis, that I don't know much, but I think the way you could interpret it as a narrative will come up in what I will do later. But I think that's...
I mean, just to put it differently, if you had come up with a very general set of models and say, okay, this is going to be my environment, and your motivation was to convince lay people, somebody could have criticized you for saying, well, but lay people don't really understand this complicated model. So I think there is yes. Given your motivation, there is an argument to make that, it's not just like this is tractable and so on, but this is the maybe right place to look at this question.
Okay, no, that's a good point. I should write that down. Yeah, so that's a good point. Thanks. So
I have one clarification. So these recursive linear models are basically, you're going to restrict attention to the reality being recursive linear or the models proposed by the researcher being recursive linear, or both?
So I think the best, if I'll give you now an example and then I'll show the model, I think then it becomes very clear. And then if it's not, then stop me and I'll explain. So I think the following example may try, maybe I'm always talking too much sort of in the air right now, but I think the following example hopefully will illustrate what we have in mind in a very simple form. So I'm going to couch it in the story of fishing for surrogate markers. Okay, so think of an analyst for a pharmaceutical firm that has data on the joint distribution of X, Y, and X2, and X2 and X3, but he doesn't have direct data on what he's really interested in, which is the relation between X1 and X3. So for example, think of X1 as drug dosage, say for osteoporosis. X3 is, say, long-term effects. And, since he's developing a new drug, he doesn't have data on its, long-term effects. However, past research have shown that, some biomarkers are correlated with the active elements in the drug and with the, long-term effects. For example, just by looking at the web, there are many potential biomarkers for, osteoporosis medicine. One of them, which I found, it's called hydroxyproline. So our analysts, can measure the relation between the drug and the biomarker, and past studies showed relation between biomarkers and long-term effects. And this is what our analyst is going to do, is going to estimate. Here's an example of a very simple recursive model. It has 3 equations. The first one is not really an equation, right? X1 is just the random variable. X2 is a linear function of X1 plus some noise, and X3 is a linear function of X2 plus some noise. So you could represent this system as the following graph, right? Basically that X1 affects X3 via X2, right? So X1 affects X2 and X2 affects X3. Since I'm going to be interested in coefficients of correlation, there's no loss in just assuming that all these variables have 0 mean and unique variance. And our analyst assumes that the error terms are uncorrelated with each other. And in each equation, the error term is uncorrelated with the preceding variables, preceding x's. So his model basically makes, and this you could see from the graph, a conditional independence assumption, right? Conditional on the biomarker, X3 is independent of X1. Okay. So let's denote by rho ij as the true underlying correlation between the variables xi and xj. So if this is our system of equations, the second and third measure the true underlying correlations between 1 and 2 and 2 and 3. That's what our analyst has data on. The model's predicted correlation or causal effect of X1 and X3 is just the product of these 2 coefficients, rho 1, 2 and rho 2, 3. That gives you the estimated correlation between 1 and 3, which here can be interpreted as the predicted causal effect of the drug. Okay, so our analyst who wants to, say, get FDA approval would like to have, as large as possible causal effect according to his model. Let's assume, just to make things simple, that in reality, there's actually no effect, okay? So the drug is just independent of long-term effects. And so our analyst can create a false correlation between the drug and long-term effects simply by choosing a biomarker that's correlated, with the drug and with long-term effects, right? The question is, how big of a false correlation can he create, right? How large can his predicted coefficient of correlation can be? If in reality the first and third variable are really uncorrelated, then if you make the biomarker highly correlated with the drug, then that's going to come at the expense of its correlation with the long-term effect, because in reality there's no correlation. And so let's try and understand how big can what's the limit, how big can this false correlation be? So think of the analyst, so he tries to, suppose there's like an ocean of biomarkers out there, so he's trying to fish for the one that's best for him. And so you can think of this as actually so instead of thinking of like choosing biomarkers, what you could think of is that he's trying to choose a covariance matrix, right? Where on its main diagonal, you have ones, because we said the variables have unit variance. At the two corners, the bottom left and the top right, there's zero, because in reality, there's no correlation. And he's trying to find the best, which covariance matrix will drive this product as high as possible, right? So we're trying to find this matrix that would maximize the product of row 1, 2, and row 2, 3, but subject to the constraint that this has to be a covariance matrix, so we need to satisfy positive semi-definiteness. And so we get that the highest fake correlation that our analyst can achieve is half. And this bound is actually tight. So in the sense that if there's really like an ocean of biomarkers out there, and for any, covariance matrix, there is actually some biomarker out there, then in fact, you can reach this bound by picking the biomarker, or X2, to be this linear combination of X1 and X3, just the square root of half times the sum of X1 and X3. So if you find such a biomarker, that's going to allow you to reach the highest fake correlation you can. So let me illustrate this actually, how it can manifest itself, sort of in real life. So what we did is we went to the World Health Organization, which has, gazillions of variables in its data. And what we tried to do is pick two variables that in reality are uncorrelated. So we picked urban expansion and death from liver cancer. And then we tried to fish for a biomarker, some auxiliary variable that will allow us to reach as high as we can the bound of fake correlation. So what we found is coal consumption, and as you can see, we can actually reach a fake correlation, pretty close to 0.5. And moreover, I can also give you a semi-plausible narrative, right? That, urban expansion increases consumption of coal, and that affects and increases the frequency of death from liver cancer. And to sort of demonstrate what I said before, the fact that, if you have an ocean of biomarkers to choose from, that can allow you to, reach sort of the upper bound. So what we did here, so we think of this that we're trying to fish for this X2. So think of this like we're interviewing, biomarkers. So they're standing in queue. And what I want to show you in a graph is, how close we get to the upper bound of the fake correlation as a function of how many variables I can interview. Okay, so what I'm going to show you is a graph. So what we did is actually we just randomly selected an order of variables, and then we fixed it. And then we checked each one and we saw what's the highest fake correlation we can get. And so we get this graph. So you could see that, we're starting with, very low correlation. When we have 50, we reach some heights and then we stay flat, and then suddenly at 200 we jump, and then again we have a jump. And again, it's not smooth because we fixed the order. And so that shows you how you can, if you have rich data to fish from, then you might be able to get pretty close to the upper bound. And so basically what we, this was just a simple example where there's only one auxiliary variable that we can use, that what I call the biomarker. But what we want to try and understand is, if you give me the, what's the true underlying correlations between the variables of interest, and give me a bound on how complex my model can be, how many variables I can put in. As a function of these two parameters, what's the highest fake correlation I can create? How does it change with the underlying correlation? Maybe if they're negatively correlated, I can't really do much. Or how does it change with the, you know, how many variables I can put in? And so that's essentially what we want to understand. And for that, of course, I'll have to give you the model. But I think this is sort of a good point to stop if there's any questions before I jump into the model.
If I may ask a short clarifying question. If you go back to your previous slide where you have these two numbers, the row hat is clearly a wrong number. Can you go again? Where is the mistake made? By whom? You know, us as being persuaded, and you know what is that we are using wrong to come up with 0.34? Sorry, 43.
Okay, so the misspecification here that you as a lay audience, you know, may not be able to test, and I'll show you exactly in the general model where it is. But basically, the main assumption in the model here is this conditional independence, that conditional on x2, x3 is independent of x1, and that may be totally wrong. So that's the crux. That's where.
So I remember you used this analogy with literature on Bayesian persuasion, but there the receiver was fully rational.
So the analogy was just to the question, right? So in Bayesian persuasion, we say, okay, I want to persuade you, but my methodology is completely different, right? I set up your information structure. Here, I can think of this as causal persuasion, right? My mean is I choose a model, and then I'm trying to persuade you in terms of the correlation. So it's a totally different question, but it's in the same spirit.
But the receiver is lay. I mean, it's a requirement because if the receiver could, you know,
so
understand.
Here the receiver again is not an econometrician, and in a couple of slides, I won't make him totally naive. I'll give him some basic misspecification test that he can run, but it's not going to be, exhaustive. But in any case, I think is a really interesting question, which right now we don't know what to say about, is, you know, the more you make the audience an expert and the more they're equipped with misspecification tests, then you're going to kill all models, right? Because we know all models are wrong. So there's a trade-off, you know, how much can we test? Because at the end, we do need to use some models. So that's an open question that we don't know. Okay, so our audience is going to do some tests, as I'll show you, but you could do more, but the question is, when do you stop? Because otherwise, none of the models will survive.
Thank you.
I have another clarification, another question. So it's going back to my first question. So basically, we started in your example assuming that the model is recursive linear, okay? And we in particular choose 3 variables, okay? So what it is wrong is that the true model is not recursive linear. Am I right?
That could be,
because,
but that's sort of outside. Our analyst, even if he wanted to, you know, to give you a precise model, right now we're restricting him only to use this class. So if the real world is not linear, then he's going to choose the best linear one if he doesn't want to do any misspecification. So any misspecification due to linearity is not something that we will call cheating, because we're not giving him the vocabulary to use a nonlinear model. So that's not. So if you say, okay, so you could perhaps expand it by allowing him to use a broader class. Still in that class, there will be a question of how I can manipulate you by misspecification of the model within the class you let me use. Okay, so the cheating is not through the linearity.
I understand that. I thought that the recursive linear, maybe I misunderstood it. The recursive linear assumes conditional independence.
No, because for example, if you just write down every equation, each equation is a function of all the previous variables, right? Then you're not making that linear conditional independence assumption that may be wrong. So the fact that you're using a sparse system of equation is where you're including assumptions that may be misspecified. So it's the sparseness. So it's not linearity, it's not the recursiveness, it's the sparsity. Okay, and that hopefully I'll have time to show you exactly formally, but this is a sort of a preview of where the,
Short question for the audience here. How would you know the extent of the mistake, given that you don't know the true correlation?
It's a question to me?
Yes.
So say that again?
How would you know the extent of the mistake, given the fact that you don't know the correlation, true correlation?
Okay, so in a second, again, right now, as I said, so far, but it's going to change in a couple of slides, our audience is passive, right? So he's not testing the speaker. So right now, the audience is just there to give a motivation for what the analyst does. And basically what we're just after is how persuasive a misspecified model can be. In a couple of slides, I'm going to give the audience at least one credibility test that he will run. And that will be, but again, as I said, it's a lay audience. So there's, the audience doesn't know the true correlation. So, we're not here to see, what extent they can catch the cheater, but actually we want to see how far the cheater can go, subject to a minor misspecification test that the audience will run. Okay.
Sorry, if I may rephrase the question. I think maybe the question is, suppose that you want to convince somebody, persuade somebody that there's some correlation somewhere. Here in this example, you know the correlation, and then you use the right model to inflate it. What if you yourself didn't know the true correlation? Maybe I think that was the nature of the question. What if you didn't know the true correlation? Then what model would you pick then to inflate something?
That's a great question, but as I said, we're after the worst case analysis, right? So I want to know the bound. I want to see whether a fake correlation is big or not. I can't evaluate it without knowing the limit, right? So I want to know how big it can be, and then I could say, well, how manipulative, were you in reality, or if you didn't know. So now I'm, somehow giving all the tools I can for the analyst, because I'm really after the envelope. Like, what's the highest fake correlation? What's the worst case analysis? Okay, so that's what I'm after. And the worst case, as I'll say, and again, our analyst, as I said, is his only, mischief is, which variables he put in his model and how he arranges them. So he doesn't tamper with the data. In fact, he proceeds like a real scientist. He says, here's the model. I'm going to take it to the data. There'll be some misspecification test, which I'll show you soon. And then how big of a fake correlation you can create. Okay? So let me maybe proceed, and then maybe things will become clearer as I move on, because I need to at least give you the model and the result. Okay? So what's the model? So the model is we're going to have a collection of random variables, x1 to xn. And x1 and xn will be the variables of interest. There's an objective underlying data generating process. That's P, that's the real joint distribution. And again, since I'm interested in the correlation coefficient, there's no loss that assuming that the marginal on each of these variables has zero mean and unique variance. And the correlation between, as before, between xi and xj is going to be denoted by rho ij. And we're going to have as a parameter the true underlying correlation between the variables of interest, 1 and n. So the parameters are going to be n, the number of variables in the model, and the true underlying correlation between the variables of interest. Okay, so that's the environment. Now, turning to recursive models, to be a little bit more precise, so we have a system of linear regression equations where for each k, the kth equation looks like this, right? So xk is a linear combination of its regressors. So xj, where j belongs to r of k. So r of k are the set of regressors or explanatory variables of xk. And the recursive structure means that the explanatory variables in the kth equation can only come from among the dependent variables in previous equations. And beta jk is the coefficient of the jth regressor in the kth equation. And epsilon k is the error term. And the beta jk's are given by OLS. Okay? So to be a little bit more precise about what our analyst assumes, so by using these models, our analyst assumes that the error terms, again, are uncorrelated with each other, and the error term in each equation is uncorrelated with all the with the regressors in the equation with all the previous x's. So the fact that our analyst uses OLS already implies that that the error term is uncorrelated with the regressors in the equation. So where the real assumption is in assuming that the error term is also correlated with all the other preceding variables, right? So this is the conditional independence assumption that may be misspecified. Okay, so this is the potential misspecification that allows our analyst to cheat, that the right, so he's assuming here a conditional independence property that may be wrong, that conditional on its set of regressors, xk is independent of all the other preceding variables. Okay, so in our simple example, it was conditional on x2, x3 is independent of x1. Okay, so that's his assumptions. And as I said, our analyst wants to estimate the correlation between 1 and n. So just to illustrate how it's done through this recursive system of equation, let's look at this example. With 4 equations, you could represent this as the following, in the following directed acyclic graph. x1 causes x2, x2 causes x3 and x4, and x4 is influenced by both x2 and x2. So to estimate, using this model to estimate the coefficient of correlation between 1 and 4, what you do is you take the last equation, the equation of the variable of interest x4, and you want to write it down only as a function of x1 and the error terms. So right now it has x2 and x3. You substitute instead for x2 and x3 the right-hand side of x2 and x3. So you get this, but you're not done because you still have x2 in there. Again, you substitute the right-hand side of x2, and then you get this equation of x4, which only depends on x1 and the error terms. So you could think of call the coefficient of x1 alpha, and the coefficient of the kth error term gamma k. Notice that each of them is a combination of these betas. And so you have this equation. xn is some alpha times x1 plus the sum of linear combination of the error terms, where the coefficients are combinations of the estimated betas. And now, as I said, our analyst treats these error terms as independent variables, and all of them have 0 means. X1 has 0 means, so the estimated mean of xn is 0 as well. But now we want to estimate, so how are we going to estimate the correlation between 1 and n? What we need is to compute the covariance between x1 and xn to estimate, well, what's the estimated covariance of x1 and xn, and divided by the product of the estimates of the standard errors. Right, so what's the variance? What's the estimated variance of xn? Right, since x1 and all the error terms have 0 mean, is just the, we just take the expectation of the square of xn. Remember, the epsilon are uncorrelated with x1. you get this alpha squared times the variance of x1 plus this sum of this linear combination of the variances of the error terms. Since we said x1 has unit variance, we're left with this. How do we estimate the covariance between x1 and xn? Well, we just take the expectation of x1 times this estimate of xn. Again, we get this expression because remember the x1 is uncorrelated with the error terms. And so essentially the estimated coefficient of correlation between x1 and xn is this alpha divided by the estimated standard variation of xn. Okay, so this is the object that our analyst wants to inflate. And as I said, I'm going to, up to now, I didn't give any role to the audience, but right now I'm going to somehow constrain our analyst so he can't just, create any model he wants. There's going to be some constraint, some minimum constraint that we're going to impose on him. And this is the undistorted-marginals constraint. That is the audience will check the following is for every, so the requirement is that for every variable that the analyst includes in his model, the model's estimates can't distort the marginals. That is, the estimated marginals of each variable have to be correct. So the model can't distort the mean of each variable and the variance of each model. Now, what's the interpretation of this constraint? One is you could think of this sort of as a simple, intuitive misspecification test that can be run by a lay audience, in that monitoring marginals is relatively easier, compared to monitoring and checking correlations or conditional distributions. So if I'm some expert and I present a model, maybe even a journalist can see that the model actually estimates, say one of the variables is inflation, and on my model estimates highly volatile inflation, where if we look at inflation, we see that it's pretty stable. Or if it's a model of, weather forecast, then if one of the variables has some highly volatile changes in the weather, but the weather is pretty stable, that's going to deem the model incredible. Okay, so this is the constraint under which our analyst would operate. So there'll be this minimal test that he'll have to pass. And as you'll see, actually, this constraint will also be helpful analytically. Okay, so I didn't say so, but the 3-variable model that I showed you before actually passes this test. So it satisfies this constraint, and hopefully I'll have time to explain to you why. And so, first of all, the fact that our analyst runs a linear regression, as we saw, that already implies that the means are undistorted. So this constraint really boils down to the fact that the variance, the estimated volatility of each variable has to be correct, cannot be distorted. It means that the estimated variance of each variable has to be 1. And so if you remember, our estimated coefficient of correlation between 1 and n was alpha divided by the estimated standard error of the nth variable, but that has to be correct. So really, the target correlation is just alpha, that coefficient of x1 in the expression of xn when we substitute everything in. So our question, so the general question that we're after is the following, is, is really, you can think of as, give me a class of models, how much can a misspecified model in that class distort pairwise correlations while still preserving margins. Okay, so translated to our model, we're really asking how big can alpha be as a function of n and r. Okay, so that's going to be our question. And then we're also going to ask, continuing the simple example I showed you before, is this bound tight. That is, suppose I give you what's the highest phase correlation that you can achieve given N and R, and that you can't distort marginals. What's the most persuasive model, right? So in our example of the biomarker, that wasn't really in question because there was one auxiliary variable that you could use, so the model was pretty much given. But now I want to know what's the architecture of the model, right? What's the graph, like the graphs I've showed you, what's the optimal graph, and what are the elements of the graph? So if you think of the graph as the narrative, the plot line, what's the most persuasive plot line, and what are the most persuasive plot elements? Okay, so that's going to be the question. So before I give you the characterization, are there any questions? Okay, so to show you the characterization, think of the variables of interest, 1 and n. Think of them as two vectors in space that create an angle, and the angle measures the true correlation between them. Okay, and how is that? Suppose that they form an angle such that the cosine of that angle is exactly the coefficient of correlation. Okay, so take that angle, so that's the arc cosine of R, and chop it up into n-1 equal subangles. Okay, call that theta n R. So this is a notation I'm going to use, and what I want to give you now a characterization is if you can choose, any model you want, that is any, distribution over the variable, or the variable. Basically, by choosing variables into the model, it's as if you're choosing the distribution, but you're choosing a covariance matrix, but you have to respect the fact that, as we saw in the example, that the true underlying correlation between 1 and n is R, and that you cannot distort the variances. So the main result is that for almost any covariance matrix where the true underlying correlation between 1 and n is R, and if the estimated variance of each variable has to be correct, has to be 1, then the highest fake correlation is just the cosine of this subangle that I presented here, raised to the power n-1. Okay, so that's the bound, that's the highest fake correlation. Notice that there is a qualifier here, a genericity qualifier, that is for almost any objective covariance matrix, meaning, think of this, that you're, as in the example that you're of the biomarkers, that you're, randomly picking biomarkers, then, by chance, you might hit one that actually passes this threshold, but the measure of such, covariance matrices is 0. And I don't know if I have time to show you why we have this, why it's for almost and not for any.
We have 5
minutes. Let me, before I stop, I want to continue just a second, because right now I gave you the bound, but as I said, an interesting question is this bound tight? Well, what is the most persuasive model? Is there a model that actually reaches this bound, right? So what's the most persuasive model? So it turns out that the most persuasive model is actually the simplest one, right? It's a recursive system of equation where each equation has only one explanatory variable, which is the preceding variable, meaning the most persuasive model is actually a causal chain where one thing leads to another. So this is actually the simplest n variable connected DAG, directed acyclic graph, measured either by the number of variables, the number of links, the click size, or the number of ancestral nodes. So that's the architecture, right? So the plot line, the most persuasive plot line is just a chain. Now the question is, what are the elements? Which elements do I put in the narrative? What are these variables? Remember before, in the biomarker example, we saw that the best biomarker was this linear combination of 1 and n. This is also true here. So essentially, the optimal model is going to be a two-factor model in the sense that every variable is going to be a weighted average of two standard normal variables. which you can think of as being the first and the last variables. And the weights are going to start so that, they start off giving full weight on variable 1. And then as you proceed towards n, the weights shift towards the second variable. And I need to pick the weights so that I get that the variance of each variable is 1, and that when I compute the correlation between 1 and n, I actually get R. And so the variables to put in the optimal model are given as follows. Each xk is this linear combination of S1 and S2, where the weight of S1 is the cosine of k minus 1 times that sub-angle I showed you before. S2 times sine of k minus 1 times that angle. So, for example, when k equals 1, I get x1 equals S1. And when you put in k equals n, and then you use trigonometric identities, you will get that the correlation between x1 and xn is indeed R.
1 minute, okay? Just a reminder.
Okay, so if I have 1 minute, then let's just look at this formula. So notice that it increases with n. Moreover, it converges to 1 as n goes to infinity, independently of the true correlation, meaning even if the variables, their actual correlation is -1, if you allow me to give a long enough narrative, have many variables as I want, I can fully convince you that the variables are actually positively correlated, perfectly positively correlated. And just to illustrate how it proceeds, take R to be equal to 0. Of course, if you only have 2 variables, you can't do anything. With 3, we saw it's 0.5. With 4, it's 0.64. 5, it's 0.73. Then it slowly climbs, but it gets all the way to 1. And then just to give you a geometric interpretation of the formula. So as I said, R cos are just the angle representing the correlation coefficient. Slice this angle into n minus 1 equal subangles. These subangles represent the correlation between adjacent variables in the causal chain, because we know that when you have a causal chain, just like we had in the biomarker example, the estimated correlation is just the product of the pairwise adjacent correlation. And that's how you get this cosine of theta 1n raised to the power n minus 1. Okay, so that's the yeah, so I guess what's left, and I don't have time, is to give you an outline of the proof, but I think I'm out of time. So at least I gave you the main result. And just to give you what else we have in the paper, except the proof, which is really nice and I can show you, is we also show the upper bound when you're restricted to use only a single equation, like we often do in economics. And of course, that's bounded away from 1. And we also show what's the bound when the variables are binary, which is also, and you can use only chains, which is also bounded away from 1. But I guess that's it. I'm out of time. So
okay, so thank you very much for the talk. So now we start the questions. So maybe Ignacio has a question. Maybe he can start, and then I think there were some questions from the audience.
Sure, yes, thank you. I have a few questions about the theorem. I know you didn't have a lot of time to go over that, but actually, I can obviously ask you offline if there's no time. I just want to make a kind of a big picture comment here of something that I think you didn't emphasize that I really like about this. There's a very large literature on correlation neglect. It goes back to Acer and Raven and Shehiel, the idea that people don't understand the correlation between the private information of others and their actions. And now, more recently, Eister and Weizsäcker, Enke and Zimmerman, the correlation neglect literature basically points out that the correlation exists, and then people don't take it into account. They don't see it. They're not able to see that correlation. They make a mistake. But something that I really like about this is that it's saying, well, on the other hand, the opposite can also happen. Sometimes, a correlation does not exist, and we make it up. We kind of, we fool ourselves or other people into thinking there's a correlation when there's no correlation. And so far, to be honest, the only way that I thought you could do that in a misspecified model was through unobservables. The typical story, education is thought to cause high income. but it could be unobservable ability, for example, that is doing it and not education, right? And that's how you generate this spurious correlation. I think there's a novelty here that you're really generating a correlation without any unobservables, through these kind of recursive models. And that's something that I think I would emphasize, that I find kind of very, very interesting. So that was a big picture comment. I'll let other people ask questions. If if there's enough time, then I'll ask you about the theorem in particular, but I'll let other people ask questions.
Okay.
I think there was a question.
So people just are going to ask.
Yeah, let
with
me
the
see.
mic.
Yeah, I think Guillermo Carmona had a question, so maybe you want to ask now, Guillermo?
Okay, thank you. No, my question was only in regard to the example you had about liver death, liver cancer.
About what?
And,
Sorry, about?
the liver cancer and
Okay.
urbanization. So I was wondering whether, without misspecification, if it was always possible to get the almost zero correlation for any possible choice of X2 variable.
Again, sorry. So the question was.
So I think. So you had this X1 and X3 variable. One was, I think, urban
population,
and X3 was, yes. And then you showed that by choosing, X3 as being coal consumption, you
X2,
could get
yeah.
very high correlation. Now, but you do this, as you explained, by having this model misspecification, especially this correlation with the regressors. Now, I wonder whether you could do, I mean, if you were, very, very honest researcher, if there is a way, I mean, how, maybe it's just, maybe just a standard question, but how is it possible for any choice of X2 to get always the same correlation if you specify the model correctly?
Wait, so if you specify, if you specify the model correctly, then you would get that there's no correlation. Right.
Okay.
So, so you could always do that. So the right model would just be that there's no correlation. I could also, if in a DAG, the correct model would be if I wrote a graph, is X1 points at X3, right? Then I'll give you the true pairwise correlation, and it will be 0, close to 0. So I could always give a model that's correctly specified. So I didn't preclude that.
Okay, thanks.
Sure. There's any other questions?
Thank you. Any other question? Yes. There's one other question. Let me see. Let me see. Well, I have Antonella. Yeah, Antonella has a question. Oops. Antonella?
Yeah, I've been promoted to a panelist. Can you hear me?
Yeah, I can hear you.
Hi. Sorry, I'm not a panelist. I'm really a lay person here, and I have a very general question. And I wonder whether your theory somewhat relates, and if so, how, with the practice of p-hacking. Could your theory, the idea that you introduce variables, you add variables to a specification, just report selectively those that have a significant p, and this seems to be a very common practice especially with big data and things of that sort. And I wonder whether your results have any relation with that selective practice of choosing explanatory variables on the basis of their p-values, basically.
Right. So I mean, as I said, what we do is related to that in the sense, as I said, I call it model hacking, in that I selectively choose, what variables to put in and how to arrange them. It's not so much about significance, because all I've done is also true if I have an infinite sample, so I don't need even to talk about significance. So it's as if I have infinite data, and so I don't need to look at confidence intervals or significance. But it's related to this opportunistic choices of, what, as I said, the sparseness of the models, what variables to put in each equations, which here effectively says, what type of conditional independence assumptions I make.
Yeah.
But it's related. That's why I call it model hacking rather than p-hack. But it's related to that.
Okay, thank you.
You're welcome.
Any other question? So Ignacio, do you want to ask again, or?
Sure, yes. If you could just put the theorem statement there. I have three questions about, I think it doesn't seem like an easy theorem to prove, so I will not ask you about the proof. This probably takes a lot of time to understand it. But I have three questions about the statement of the theorem to help me understand what it says. Okay. So the first one is, let me make the three questions and then you can answer any of the three that you want, or But the first one is that there's a constraint here. You're looking only at models where the variance the fitted variance is correct. And I wonder to what extent that already reduces significantly the set of recursive models. We know it's not empty because you told us that you can get the tight bound. So we know at least the simplest DAG, it satisfies this assumption. But I wonder, is that the only one that satisfies that restriction, or the other ones? And I can tell,
So let me here. So step one. So there's three steps to the proof. The first step exactly answers your question, which is the requirement that I don't distort the marginals, and in particular, not the variances, implies that the DAGs I can use is a specific class, and it's the class of perfect DAGs. So perfect DAGs are those DAGs where any pair of parents that have a common child have to be married.
Okay.
So, for example, we have example of a perfect and imperfect.
Okay.
So that's already so that's why it's very helpful, as I said, that constraint. And then the next step is that we show that that once I have perfect DAGs, there's no loss in looking at chains. That give me any perfect DAG, and the variables you put, I can mimic the correlation with the chain that's not longer.
Okay, so it's not, the result is not a unique way of getting the tight bound, but but I guess, yeah, okay, got it. Thanks.
Yes.
Okay. The second quick question is more about the implementation of, this is maybe something a computer scientist might be interested in, but you said that as n goes to infinity, the correlation goes to 1, if I remember correctly. So something that comes to my mind is that as n goes to infinity, also being able to find variables, because we're talking about many, many more equations now where you're trying to find these perfect, complex combinations of variables, that presumably becomes harder and harder. So there's a question, with big data, can we really get to that correlation equals to 1 or not? But maybe that's more of a computer scientist kind of a question.
Yeah, so actually, yeah, so it's a good question. So the third co-author, Yair Weiss, is actually a computer scientist from Hebrew U. And he, what we learned from him is actually in many in many fields, I mean, not in many, but in fields like biology, for example, or you don't, the way they proceed is usually they don't propose the model. They use algorithms to find the best network. So they learn what they do is they propose the variables, but they let the data tell them what the graph is. But what they do is all the algorithms they use look for trees, which are perfect DAGs. Okay, so perfect DAGs have, I guess, some nice computational properties that it's easy to find. So in fact, so our theorem, for example, if you say, if you restrict yourself to these algorithms, so you don't propose the model, you just propose the variables, but you use these algorithms to try and find the model, then we don't need that qualifier for almost, it will be for every, covariance matrix. So you're right that there's a computational issue, but it turns out that for, I don't know if n goes to infinity, how badly things go, but the but perfect DAGs are computationally convenient, and that's why in many of these studies that look at Gaussian Bayesian networks, they always restrict themselves to perfect DAGs.
Okay, great.
But
Thanks.
I can give you more detail about, really.
Sure. Let me skip my third question because I see in the chat there's somebody who wants to ask a question as well. So
Okay.
We have a question from Emre Timur. So go ahead.
Yeah, hi, thank you. So I was thinking the main result is quite pessimistic, that you can get basically anything you want using manipulating models. Is it possible to make it a bit more optimistic if you think that the layman will be more easily persuaded by like simple models with small n? Because I guess with small n, you cannot manipulate that much.
Yeah, so I showed you that, how you can see the rate at which the false correlation grows. So, I mean, it can get pretty high already, I think, if they're uncorrelated, if I go back to the, here. So, I mean, even with 4, it's already, not negligible, or with 5, but, I can't get all the way to 1, that's for sure. So the n is restrictive. It just says, the more you allow me to put in, the more persuasive I am. And yeah, so that's, but you're right that, if I, for example, if I only allow you to use just one extra variable, then the most you could do is half. But what we're saying is that even if you have somebody who sort of, I think the message sort of, we're saying that even if you have somebody who sort of, proceeds scientifically, right? So I think, he's not playing with the data, he's giving you a model and he's saying, I went to the, I think we all, not that I'm, literally saying that our model applies to this, but I think recent events have, showed us how, different policies have been proposed based on, mathematical models, and different countries use different models and arrived at different conclusions. And so but it was always this pretense that, we're basing our decision on science, right? Because I wrote down a model and I used the data that was available. And so we were just saying that we need to be a little bit worried that even you sort of proceed scientifically, there's still room for manipulation. But on the other hand, if we're subject models to, an array of very, a long list of misspecification tests, at the end, we're going to kill every model. And that's also not something we want to do. So I think an interesting question is, like you said, you can't use too many variables. So an interesting question that we don't know yet how to approach even is like, what's the right balance, right? What's like how do you do this trade-off between, allowing some models that maybe are, can manipulate, but on the other end, you want to have some models so you could actually say something. So we don't know yet, how to approach that.
Thank you.
Thank you very much. Well, it's already time, it's 6:15. So thank you, Kefir. Thank you, Ignacio, for participating today with us. Thank you all attendees. So we hope to see you next week.
All right, thanks.
Bye.
All right. So thanks a lot, guys. Thanks a lot for having me. I really enjoyed it. Wish I could have more time, but still, thanks very much.
Should we just wait a few minutes,
Sure.
a minute or so, yeah?
Well, I think it's fine. I mean, we can just say thank you and goodbye.
Yeah, okay.
I have a question, Kefir. I didn't
Sure.
make because we're running out of time, and it's related actually to the last question. So basically, the leverage that the number of variables gives you is because you can play with the matrix of correlation between the new variables that you add, right? So to some extent, it seems that if you can't limit that correlation because you have additional information, there's little harm in adding these new variables. Is that true?
Say that again.
If you already know the matrices of correlation between the new variables that you are adding, okay, not with the first variable and the last variable, the ones you're interested in, okay, but with the existing variables, okay, that should limit how much you can distort. No, it's like, for instance, I was thinking of the example that you were giving at the very beginning. This example using the data set from the World Health Organization. Okay, that example, I remember you were only adding one variable at a time, if I got it right. But you could think of adding all of them in sequence at the same time, increasing the number of variables that you add. But when you do so, you can also control for the matrix of correlation between the new variables that you are adding. Okay, and that in principle should limit how this bound that you have computed should increase. Is that correct, or am I getting it wrong?
Again, if you have if you have a rich pool of variables to choose from, and meaning that you could get pretty close to these optimal variables that are displayed in the theorem, then it's not going to restrict you, right? So unless you have something in mind where the audience knows something, but if it's the analyst, the analyst, if he's free to choose as many variables as he wants, and there's a rich enough pool of variables to choose from, then that doesn't constrain him. Right, what could constrain is if the pool of applicants is not so rich, right? So if, say, for osteoporosis, if the studies have shown that there's only like 4 biomarkers you could choose, then that's of course will constrain you. But in fact, at least our understanding of the medical literature, that there's an ongoing debate about this practice of biomarkers, because if you look at some papers in like the New England Journal of Medicine, they know that there's this room for manipulation, but right now they don't have an alternative, right? Because if you want, just like I said, you need some models. So if you want to introduce new drugs in the short term, you don't have data on their long-term effect. So right now there's no alternative but using biomarkers. But the medical literature, people have made their careers by just finding new biomarkers. So at the end, when you think about some disease, there's a lot of potential biomarkers you could choose. And right now they don't have like test, oh, this is not a good biomarker and this is, right? So that's like something they're trying to cope with, how to do that.
I see, I get it.
But again, that's a simple model where there's just one extra variable.
By pure coincidence, on Monday, there's another webinar that we organized with Francesco, and when we have Ines presenting a paper together with Gilad and Ronnie about persuasion and correlation neglect.
Yes, I know that.
So that was Ignacio was talking about the neglect rather than blowing up the correlations. But it's funny how a lot of people work on similar issues. No, and Gilad last week presented a paper on misspecified models in votings.
Oh yeah, I know that paper with Ronnie and this econometrician, macroeconomist from LSD. I forgot his name. Yeah, so I think it's actually nice that you've included, because I think this is a very nice new literature about model misspecification, and I'm glad that you actually have included some of the exciting recent papers there. I think it's a really interesting literature. So thanks very much.
Thank you.
Thank you again.
Thank you. Here. And hopefully we'll get to see each other in person.
In normal circumstances.
Yes.
Thank you very much.
Thank you. Bye.
Bye.
Thank you. Bye.
Bye. Bye.
Okay. See you.
Bye-bye.
Bye.